Good morning, everyone. So, I'll cover the applied optics part with this few online courses, which is part of your DEC, DSE. And syllabus will be covering on this section as sources, detectors, basic principle of LEDs, various kind of LEDs, lasers, then the various kind of emissions, laser absence, type of lasers. Beyond it, we'll be covering photodetectors, holography, fiber optics, among other things. Now, this section is only covering some review about semiconductor physics. Then we'll jump into LED. So, this is the recommended listed book. A large part of this text is actually covered from SMC. Some with some help from my senior in IT Rookie. So, we need to understand that semiconductor light sources for semiconductor light sources, generally a p-n junction works as a active like recombination region, and when it's forward biased, then the electron and holes they come and recombine with one another, and radiatively or non-radiative. So radiative ones are the like they emit photon, which is basically the LED operation, and non-radiative ones are basically thermal. Whereas laser is a step more where we're using a resonant cavity to achieve a coherent, highly directional optical beam with narrow line width. Get to that. Before that, we need to review some of our basic semiconductor physics. I'll not be going into any of this detail, just a few equations to recapitulate so that we are not lost in the middle of the course. Some of this thing is basically carrier concentration and Fermi levels, which you already know that with like how do you calculate the number of electrons using density of function and Fermi level equations, density of states. So I'll not go into detail of this because it's not important right this point. But the Fermi Dirac distribution is definitely important because so if there is a question that what is a Fermi level, so it's basically the highest occupied level in any system. So generally, if you consider this one, so it's completely filled state. So if you have E equals to EF, then this function becomes one. So the distribution function becomes one. So there's a temperature variation of this function, and we can calculate the carrier concentration from using this one. And eventually we need to get to the carrier concentration. And an idea about the energy difference between the conduction band energy to the Fermi level energy. Now, an important concept is for intrinsic semiconductor and finite temperature, thermal agitations occur, which results in continuous excitation of electrons from valence band to conduction band and leaving an equal number of holes in valence band. So that's normal in a normal state. This process is balanced by the recombination of electron electrons in the conduction band with the hole in the valence band. So we're talking about equilibrium process. Now, for steady state or equilibrium process, as I said, so the N and P, which are the carriers, are generally equal to the intrinsic carrier concentration. Now we can find out an idea about this N and P, which is for a P type or an N type, with the use of EF. So we get the intrinsic carrier concentrations. And an idea about the intrinsic carrier concentration of silicon and gallium arsenide as a function of reciprocal of temperature. So you can see that it changes heavily with temperature. This diagram is more familiar, and many books actually go through this kind of diagrams so that things are more easier to understand for students. So it's an energy level diagram. So this thing is an energy level diagram, showing the excitation of an electron from a valence band to a conduction band. So this is your valence band, this is your conduction band. So if you have a transition of one electron, it gets excited and it reaches to valence band. Then this is more or less free, so it can start moving with the effect of the electric field. Now, we also need an idea about the equal electron and hole concentration in an intrinsic semiconductor. So if we think about the electron density, then you can see that these two are equal, like the hole concentration distribution and the electron concentration distribution are equal. And this Eg is the band gap. We're talking a lot about conduction band, valence band, and band gap. So it's good to have an understanding. And how to like deduct them is not important in this course. It should have been taught in your basic electronic courses. Now, if you think about a schematic of a band diagram, this is like this. And if we think about the density of states for intrinsic semiconductors, Fermi-Dirac distribution, carrier concentration, as I mentioned, it's same for similar to exactly the intrinsic carrier concentration for both. The magnitude of the impurity ionization energy can be also calculated from the hydrogen atom models, but not that important. This is rather more important, which is a donor and acceptors. So, so what happens is you have a silicon crystal without any impurity, and then you have one N-type one where you actually put a donor, which is a P atom, and for acceptors you put in a negative one, which is a boron. Now it creates donor and acceptors levels, which are helpful. Now these ionization energies for donors and acceptors, they largely define that which kind of material we'll be using for the devices we need. But most of the cases we are using silicon, which is element, which is a group 4 element, and gallium arsenide, which is a combination of a group 3 and a group 5 element, which you say like 3 5 semiconductors. And so a easier way to understand this one, like the N-type semiconductor, is donor level is closer to the conduction band, so an electron doesn't need too much of energy to jump to the conduction band. It's actually for n-type, it's the opposite way. So what happens is you have a donor level here, and that already has electrons which jumps to the valence band. So whereas for acceptors, you have acceptor level near the valence band. Now intrinsic and extrinsic materials can be further, so we'll be dealing a lot with intrinsic and extrinsic materials, and as you understand that a perfect material, like without any impurity, is intrinsic material, and here the N and P type carriers will be same as the intrinsic carrier concentration, which can be given by this, whereas Eg is the band gap. For extrinsic material, which is a donor or could be an acceptor type, it follows this equation, which is basically the mass action law, that N and P type like concentration of carriers is equal to the Ni squared, which is the intrinsic carrier concentration. Now the majority carriers are electrons in N-type, hole in P-type. Minority carriers are definitely the opposite. For a device operation, we need to inject or extract minority carriers. For extrinsic carrier, I'm not going into detail of these equations. But definitely we have to understand that in extrinsic carriers, what happens? For extrinsic semiconductor, we have this kind of donor levels, which is created because of the addition of impurity atom into this thing. And so definitely you don't have the same carrier density as earlier. So the carrier concentration is changing. Now this is more or less a familiar diagram. Which is of a p-n junction. So what happens is you have a p-type material and an n-type material. You bring them close to each other. And because of the carrier injection across this layer, what happens is it starts creating a depletion region. Now, the impurity concentration in a semiconductor changes abruptly from acceptor impurity to a donor impurity and obtains an abrupt junction. So even if you find this diagram a bit complicated, this is much more easier. So what happens in the depletion region is, because of the diffusion across this junction from p-type, the diffusion is for the positive charges, which is the holes, to this region to N, and electrons from N to P. After a certain time, the recombinations are not sufficient to actually make this go away, and it starts charging up like space charge. This region starts accumulating more and more like electrons, this more and more holes, and they prevent more electrons to come from here to this direction and more holes from here to this direction. So this region becomes more or less the depletion region, and it creates a barrier potential which restricts this minority carriers to further diffuse into the regions. Now, a reverse bias PN junction definitely increases this depletion region further, whereas a forward one actually takes it away. So you have a current flow across the junction, then you have forward bias. Now, we do have the drift current density for PN junctions, and also it has a diffusion component of it. So overall, the current density across this has two components. And with that, we can actually find out some important, like this built-in potential. So the IV characteristic of a PN junction is definitely important. And what happens is it increases the current until a certain voltage, then it actually saturates somewhere here. For reverse bias, it actually, so the current stays same after a certain time. So even if you increase the reverse voltage. These experiments are already included in most of the PSC courses. The other part which will be important, particularly for light emitting devices, is recombination, generation, and carrier lifetime. So what we understood till now is whenever the thermal equilibrium condition of the semiconductor system is disturbed, that is the P into N is not equal to the Ni squared. The process exists to restore the system to equilibrium. So it puts it back into the same mass action law. And these are recombination or thermal generation depending on the situation, depending on either this situation or this situation. So for recombination, for band-to-band recombination, the energy is exchanged to a radiative or agar process. So radiative are this ones, which is a photon emission. Agar process are this ones. Recombination from single level traps. So if you have a trap within the same level, then it's generally non-radiative, which is thermal. This is the concept which is used in light emitting diodes. In any semiconductor, electrons or holes can meet simultaneously, like spontaneously, and recombine. That is, conduction electrons can fall down and fill the holes in a valence band. And excess energy is then released as a photon. This is the process to emit a photon. At low temperature, the concentration of the carriers, even in doped semiconductor, is too low for the carriers to meet and recombine simultaneously. However, we electrically inject carriers into the semiconductor, we can raise their concentration dramatically so that the probability of recombination becomes much higher. We can observe emitting photons, and that is a p-n junction diode in forward bias region. If we inject a higher concentration of electrons into the n side and holes into the p side, these carriers can meet at the junction and recombine with releasing photons. This process is called electroillumination. So the kind of light emitting devices that we need to understand is light emitting diode, where electrically we are injecting electrons and holes that recombine at the p-n junction, leading to a spontaneous emission. The other part that is important to us here is the laser diodes, where extremely high carrier injection level can lead, combined with a positive feedback, a pair of mirror, an optical cavity, to a stimulated emission or lasing. So this requires for some understanding of the band-to-band transitions, which are more probable for direct bandgap semiconductors. which are more common among 3 to 5 components. In this kind of transitions, the recombination rate is proportional to the product of electron and hole concentration and given by this. Now, whereas we need to understand that recombination coefficient is related to thermal generation rate also. So this is recombination coefficient and this is the thermal generation rate. And the recombination coefficient is a function of temperature and also dependent on the band structure of the semiconductor. A direct band gap semiconductor being most efficient band-to-band transition has a much larger recombination coefficient than an indirect band gap semiconductor. In case of thermal equilibrium, we already know this equation and we understand that the recombination rate is same as this G, which is the thermal generation rate. So the net transition is 0. Under low level injections, this changes. So what we have is a carrier lifetime for holes in a p-type material. Now, we also need to know the crystal structure, particularly how the energy bands are formed in solid, which is basically comes from the orbital splitting that we already understand. So if you think about the energy level because of the orbital splitting in any atom, which are these, then in a crystal, you have thousands or maybe million of these atoms. So we are talking about many of this like levels. So these are energy levels which are very close to one another, and they're so close that they form bands. So instead of levels here, we have bands when there are too many levels. So these form the conduction and the valence band. Now, direct band gap semiconductors, like if you consider that in a EK diagram, which is energy and momentum diagram of a direct band gap semiconductor such as gallium arsenide, we have that the wave function is allowed to exist in the crystal. So it's simply the minima. So if we compare it with indirect band gap semiconductor, then what happens? That the minima of so it's a gallium arsenide, which is a direct band gap material. So the conduction band is directly above the maxima of the valence band. So in case of a recombination in this kind of a system, like electron jumps from the conduction band to the valence band, the advantage is that the laws of conservation for momentum and energy are actually valid. Whereas for an indirect gap material for like silicon, the minima of the conduction band is displaced the maxima of the valence band. So it's an indirect gap material. And so if you have a recombination in this kind of a process, then though because of the emission of the photon, the energy conservation is maintained, the momentum conservation is not valid. So this should be a familiar diagram, which is for indirect band gap like silicon. You can see that the minima of the conduction band is away from the valence band. Whereas for a gallium arsenide, It's exactly like in the same case space.